Good morning. We're going to be working on lesson 1-7 today for quantitative reasoning course, and it's all about portion control. So let's go ahead and I'm going to share my screen so we can get moving. You should be on page 107 of your course pack. And just kind of summarize what's going on here. So let's say Mrs. Main decided to bring in some donuts to our class, and there's 24 people, including Mrs. Main, of course, in the course, and I brought in 4 dozen donuts. So how could I fairly share out those donuts with everyone? So I have to know how many donuts total. So that 4 dozen, there's 12 donuts in a dozen. So I have 48 donuts to share. So it looks like with the 24 people, we can each have 2 donuts per person. Okay. But what if I only had 46 donuts to share? Then not everybody quite gets 2. But how do I decide? I mean, I could cut them up into smaller pieces, but sometimes we have items that we're trying to share with other people that we cannot break apart. Those items are called indivisible. So if in your household, you have only 1 or 2 bathrooms and you're trying to share those with other people to take showers or baths, you have to allocate those, right? The same with computers or laptops or TVs. In our household, it's TVs. If we only have 2 TVs and we all want to watch a TV show and there's 5 of us, then we have to decide who's going to get to watch TV when. And so that's what we're going to be working on today. So let's go to the bottom of page 107. It says the most common example of apportionment is the United States Congress. There are 100 senators in 50 states, so each state gets 2 senators. But in the House of Representatives, which is our Congress, our House of Representatives, the number of representatives is based on the population of the state. There are 435 seats in the House, and they're divided according to population. For example, Florida has 25 seats, Pennsylvania has 19, and Rhode Island has just 2. So because Rhode Island has a much smaller population, they only have 2. So why can't we just divide the 435 by the population to find out how many representatives per person, then multiply the state's population? Well, it's against the law to break apart politicians into people. And so we have to somehow decide who's going to get an extra representative, which we call a seat in this case, and who's going to get one less. So apportionment here is the process of fairly assigning identical indivisible objects among individuals entitled to shares that may be unequal. So let's go through this again. Apportionment is the process of fairly assigning identical individual objects among individuals entitled to shares that may be unequal. That's what we're going to be doing in this lesson. We just pointed out that the most logical way to attack dividing up the seats in Congress would be to divide the entire population by the number of seats. This would tell us how many people on average would be represented by one congressperson. This number that we're going to work with today is called our standard divisor, and it plays a really important role in apportionment. So we'll highlight the formula next, but don't think about memorizing it. Think about what it means, and you'll have a much better chance of understanding the lesson. So throughout this lesson, we'll refer to objects, the objects being assigned as seats. So like if we were assigning computers or assigning bathrooms or TVs, that's what we're going to call the seats. And the individuals they're allocated to, this time we're going to be called the districts. Or also we're going to call them the cities in the districts in this big city. I'm sorry, the districts in it's one big city. So the one we're going to work around today, it's one big example, and it's all about this large city. They have a total population here of 240, and it's in thousands. So we're going to remember that it's 240,000 people in their city. And we're breaking the city into different parts, okay? Or neighborhoods, you might think of it as, but we are calling them districts. And each district is going to get some of these 20 seats. So it says here, we're allocating 20 seats amongst these 5 districts. It says, explain why it wouldn't be fair to just assign 4 representatives to each district. So if I took the 20 seats and divided by the 5 districts, that would be 4 seats per district if they each got equal. But this is not fair because you can see that District 2 has 80,000 people in it and District 5 only has 20,000 people in it. So the districts with a larger population are going to feel like they should deserve a little bit more representation. And so that's not going to work. We're going to need a different way to do this. Remember that this is 80,000, this is 20,000. These are all in thousands. So make sure that you're remembering that. Okay. So number 2 says, find the standard divisor for this apportionment and briefly describe what it means. So we're going to standard divisor. Our formula at the top of page 108 says the total population divided by the number of seats. Okay, so total population for that city is 240,000. This is total population. And we're dividing by number of seats. And we said we have 20 seats to share. So if we divide this out, that means that there are 12,000 citizens, we'll say, people in the population for every 1 seat. And we also call that a representative. Okay. So if this were computers, it would be 1 computer for all 12,000 people to share. That's kind of how we would think about that. Okay. So it says, notice that District 2 has exactly 1/3 of the population. So let's go back to District 2. They have 80,000 people out of 240,000. So 80,000 out of 240,000. That does reduce to 1/3. It would then seem fair and reasonable then that they should get 1/3 of the 20 seats, right? Why won't District 2 get exactly 1/3 of the seats? Well, 1/3 of tells us to multiply by 20. And when we do that, that says they're going to get 6.67 seats if I round it. Remember we talked about earlier, that means that they're getting 6.67 representatives. We can't have part of a person. So we cannot have part of a representative, right? A person. So that means that we're going to have to somehow decide if District 2 is only going to get 6 seats in representatives or if they're going to round up and get 7. That's going to be the main discussion and debate all for this whole lesson. So let's go to page 109. We're going to kind of work this out. Remember that the did you get it's are separate problems. The cool thing about the did you get it in this lesson is this one did you get it starts with a new scenario and works all the way through the lesson. And the answers are at the back of the lesson. So I want to remind you, if you want an extra one to work through, then you can do that. And their answers are found in the portfolio section at the very bottom of the page. So you can work through that when you're all done. Now, page 109 here, let's go through this example. So first we have describing what is the population of the district divided by the total population times total number of seats. Well, this right here is the fraction that represents the percentage of the population that lives in a particular district, and then multiplied by number of seats. That gives us the number of seats that we're going to allocate towards that particular district. Let's look at B. It says simplify this fraction, population of district divided by standard divisor. Okay. So if we take population of the district divided by the standard divisor, it's the same as the population of the district. And then using our definition of standard divisor from page 108, it's the same as total population divided by total number of seats. So now we have a fraction, right? This is really population of district over 1 over this total population over total seats. Okay, so we have a fraction divided by a fraction. Now, this is back in the little review section, the prep section. when you have a fraction divided by a fraction, it's called our keep it, it's KFC, keep it, flip it, and change it. You're not going to have to do this by hand. We're going to work through this all on Desmos today, but it's good to understand why it's working out. So keep it means the first fraction, we're going to keep it as is. And that's right here, population of the district over 1. Flip it means the second fraction, we're going to flip it. So that means the total number of seats is going to go on top and the total population will go on bottom. So now we have this multiplication because the change, it says we're going to change this division to be a multiplication, which we did. So now when we multiply it straight across, we have the population of the district over the total population. So that becomes what we had up here, right? Times the total number of seats. So A and B actually become the same thing. So instead of looking at the proportion for a district times the total number of seats, we can just take the total population of the district and divide by that standard divisor once we have it. So number 4 says, perform the calculation in part B of the solved example for District 3 in our example problem. Then write a description of what the result of the calculation tells you. So we have the population of the district. Okay, and that is, they wanted us to do this for District 3. So District 3 has a population of 41,000 times the total number of seats, 20, over the total population. Okay, and so we multiply this straight across, we get 820,000 divided by 240,000. And divided by 240,000. Let's see if I did this correctly. We have 3.42 seats. Okay. So we can use this formula down here. The standard quota is the population of the district divided by the standard deviation. So the standard quota is what each district should get if things worked out correctly. Standard quota, that's what this is for District 3. Okay, District 3. So number 5 says, find the standard quota for each district in the city described on page 108. So each of these here. So I'm going to create a new little table for myself just to keep it organized. District 1, 2, 3, 4, and 5. And their population of the district in thousands. So I'm going to just write it out with thousands because I like to have that in front of me. And then we're going to calculate the standard quota for each district. Because just like we came up with District 2, we said we're not sure if they're going to get 6 seats or 7 because we have to do some rounding. Likewise, in District 3 now, we're going to have the same issue. We don't know if they're going to have to round down to only 3 representatives, 3 seats, or up to 4. Okay, so we know that 3 is 3.42. We calculated that above. And we know that 2 is 6.67. Okay, so I'm going to go to Desmos for a moment here. And so here's my Desmos screen. And what I'm going to do is I'm going to create a little table because we're going to use this all throughout today. So I'm going to put in my table my district populations. That earlier too. Okay, so then up here, remember, I'm going to edit this because I want to give it directions. I want to delete, I'm going to backspace and I'm going to tell it to take whatever you named the first column minus X1. Now it's okay that everything went away. Don't do anything here, but we want to take X1 and we want to divide by the standard divisor, which is divide by 12,000. And now all my numbers come back and it actually does this calculation. So it uses X1 and then it uses this recipe that I told it up here to divide by, take X1, whatever value is in X1 and divide by 12,000. Okay, so you can see that District 2 has the 6.67, just like we had rounded, and District 3 has 3.42, just like we rounded. So District 1 has 2.67. District 4 has 5.58 and District 5 has 1.67. Okay. So if we go back to our workbook page here, I'm just going to move to page 111 for a moment. So it says, now that we know how to almost find the number of seats that should go to each district of apportionment, is about deciding if each district's number of seats should come from rounding its standard quota up to the next bigger whole number or down to the smaller whole number. So that's really pretty much all we're going to do for the rest of this lesson. We've got 3 different methods for deciding how we're going to round. So the first says, round each of the standard quotas you calculated in question 5 to the nearest whole number. Then add the results and explain why that won't work as the number of seats assigned to each district. Okay, so we're going back to question 5 right here, the table that we made. And we are going to use, it says round. So we're going to use natural rounding. Okay, and natural rounding is 0.5 or bigger, you're going to round up. So this 0.67 is going to round up to 3. This will round up to 7. 0.4 or smaller, we round down, or less than 0.5, we round down. So this is 3, this rounds to 6, and this rounds to 2. And if we add these, if this is how we allocated, we would end up with 21, which we cannot have too many. So we calculated 21 seats, but we only have 20 to give out. So that's not going to work. We got to find one of these has to decide not to round up like we thought, or round down. In our case, we need one to not round up because we need one less. Okay. So the methods of apportionment that we're going to study are all based on first calculating the standard quota, then deciding whether to round up or down. So for any district, the lower quota is the result of rounding the standard quota down, basically just removing the decimal on each of these and just using the whole number to the left of the decimal. And then the upper quota is the result of rounding up to the next larger whole number. So I'm just going to rewrite our standard quotas that we had here, and we're going to look at what it means to find the lower quota for each and find the upper quota for each. Okay. So the lower quota, like I said, is just by getting rid of the decimal part for each of these here. Okay, so this one is just going to be 2, 6, 3, 5, and 1. And the upper quota is if we were to round all of these up to the next largest whole number. So basically taking our lower quotas and adding 1, it would be 3, 7, 4, 6, and 2. So now we're ready for our discussion on that. Okay, So let's go ahead and flip the page. So the two that we're going to look at are going to be Hamilton, Jefferson, and Webster. Okay. So it says the first method we'll study is Hamilton's method, which was approved by Congress for use in 1791, but was never actually used since President Washington vetoed the bill. So that never actually got used. Okay, so you can see here is Hamilton, and then we have Thomas Jefferson. That's going to be the next one. Okay, so Hamilton's method says assign each district the number of seats according to its lower quota. If this adds to the right number of seats, you're done. Okay, so let's check that out. So if we add the lower quotas, 2, 6, 3, 5, and 1, we get 17. That's not really what we wanted. Right? This only adds to 17. Okay, so we have 3 more that we can actually round, that we can actually give out. We got to decide what 3 of the 5 here are going to get the extra ones. Okay, so if it does not, that's our case. Assign each extra seats one by one to the districts in descending order of size of the fractional parts in their standard quota. For example, if 3 districts have standard quotas of 2.93, 4.7, and 3.15, the first extra seat would go to the district with fractional part 0.93 because it's the closest to rounding up. And the second one, the second extra seat would go to the district with fractional part 0.7. So it says use Hamilton's method to apportion the seats for the city described in the class portion of this lesson. In completing the table in question 7, you've done most of the work already. Cool. Make sure you clearly write out how many seats each district gets. A table wouldn't be the worst idea ever. Well, we've already created a table. So we have to go by, we have 3 seats to give, and we have to decide by the highest decimal part. So this has 0.67, 0.67, 0.42, 0.58, and 0.67. So it looks like 0.67 is the highest, and lucky for us, the 3 that have the 0.67 are exactly the 3 that we need to, in addition to make the 20. So that means these 3 districts, 1, 2, and 5, all get to round up. So we're going to use their upper quota. So 3, 7, and then District 5 gets to 2. That means that districts 3 and 4 are going to stay with a lower quota value of 3 and 5. And if we add these, we get to 20. So that would be our perfect allocation using Hamilton's method. Okay. So turning to page 113. It says the apportionment method that was adopted by Congress after Washington's veto in 1792 was designed by Thomas Jefferson, and shockingly is called Jefferson's method. It's a bit more complicated than Hamilton's method. It uses what we call a modified divisor. So right now we're using the divisor of 12,000, but we're going to have to modify that because when we use 12,000 with natural rounding, we only allocate 17 seats and we need to allocate 20. So the idea is to make sure that every district gets its lower quota. We know that won't work in general because usually the number of seats will add up to something less than the correct total. And Jefferson's method will make the quotas get bigger by making the standard divisor lower. Okay, so remember when we go to, I'm going to show you in Desmos. In Desmos, taking numbers, so we take 32,000 and we divide by 12,000 like we had up there, and then we take 32,000 and we divide by something smaller. It makes it closer, so we go from 2.67 to 2.9. So we need something, so that's where that gets that bigger. So 32,000, let's say we divide it by 10,000. Now we've got 3.2, so its lower quota would be a 3, and that would be good because we want those to get an extra seat. Okay, so that's kind of what we're looking at here. Okay, so let's go to page 113 again, and we're going to go over Jefferson's method with our thing. So it says, assign each district the number of seats according to the lower quota. If this adds to the right number, cool, but we know it doesn't. Then it says if the sum of the lower quotas, you know what, I didn't go back to my paper, did I? I wanted to read this with you. So if the sum of the lower quotas is less than the number of seats, choose a modified divisor that is less than the standard divisor and recalculate the lower quotas. Use this as the apportionment if the lower quotas now add up to the number of seats, total number of seats. If not, adjust the modified divisor again. So we know that 12,000 does not work, right? This 12 is really 12,000. So they're telling us, let's use 11 as a modified divisor, which is really 11,000. Okay, so we're now going to take our population in the districts and we are going to divide by 11,000. And we're going to go back to Desmos so you can see how to do that. So in Desmos, I'm going to click right here and it's going to let me do another calculation with X1. So I'm going to say X1. Now I want to divide everything by 11,000 and see what comes out. So on page 113, we're going to fill in 2.91 for my modified divisor now for District 1, 7.27, 3.73, 6.09, and 1.82. Okay. Then we have to use our modified lower quota. So let's go back to the paper here. Sorry for all the flip-flopping. So now we're going to use from these modified quotas, we're going to find our lower quota. So remember, we're dropping the decimals and we're just using the whole number to the left. So this would be 2. District 2 now rounds to 7, so that's good. 3, 6, and 1. Add up the modified lower quotas. Does this apportionment work? So if we add these up, we get 10, 18, 19. So 19, we still have 1 extra. Okay, so we're going to have to lower our divisor again because we were at 12,000. We lowered it to 11,000. We got 2 to bump up, but we need another 1 to bump up. So if we turn to page 104, it says our next attempt will be to change the divisors we're using. Do you think we should make it bigger or smaller? So we should go smaller. So we bump one of the districts up. So it says try again with a modified divisor of 10.5, which is really 10,500 in Desmos. So let's go back to that. Okay, so I'm going to add another column here. And again, I'm going to take X1 and divide by 10,500. And there we go. So let's go ahead and write down our modified quota, 3.05, 7.62, 3.9, 6.38, and 1.9. Okay, so this is with the modified divisor of 10,500. Let's see. So if we use our lower quotas here, we have 3, 7, 3, 6, and 1. So that gets us to 20. Yay. So this is our allocation. 3, 2, 3, 7, 3, 6, 1. Exciting. Okay, so it says we already know from question 6. Oh, whoops. We didn't talk about what happened with Jefferson's method. So it said Jefferson's method was used in Congress until 1842, when it was replaced with a new method devised by Daniel Webster, a distinguished congressman, senator, and 2-time Secretary of State. Webster's method also uses modified divisors, but it is based on standard rounding, rules of rounding than the lower quotas. Okay, so here is Webster's method. Assign each district a number of seats by standard rounding. Rounding up if the fractional part is 0.5 or greater, and down if the fractional part is less than 0.5. If the sum of the seats is equal to the number of seats available, use this as the apportionment. If not, modify the divisor and try again. If there are too many seats assigned, use a larger divisor. If there are too few seats assigned, use a smaller one. And everything is based on standard natural rounding. Okay, standard natural rounding, no lower quotas. Okay, so now we are at 115 here. So it says we already know from question 6 in the class portion that using standard rounding rules won't work for the apportionment because it resulted in 21 seats, right? When we naturally rounded, many things rounded up. So we can skip right to step 2. Since we have too many seats, we should try a larger divisor so things don't divide and create a bigger number. So I'm going to go to Desmos and we're going to use 12,500 and see what comes up. So I'm going to go to Desmos, and don't worry, if you go to the class recordings, you will see that I have put a link in the class recordings under lesson 1.7 down in JetNet under the date that we did 1.7. I put a link to the Desmos work, so don't worry there. So I'm taking X1 and I'm dividing by 10,500. Okay, so my modified quota 3.0, 3.05, 7.62, 3.9, 6.38, and 1.9. And our modified rounded quota using natural rounding and so we have, this one's going to round down to 3. This one will now round up to 8, up to 4. What do I have here? I just want to make sure that this should be 10,000. Oh, I should have done 12,500. Daggone it. I think we're, make sure I'm sharing my right screen with you all. I want to share my Desmos. I did 10,500. That's not what we are supposed to do here. I was supposed to do 12,500, Mrs. Main. Okay, so back to my paper. I need to make sure that you all have that corrected. So these are not correct. I'm going to write them up here. It's 2.56, 6.4, 3.2. Hey, I apologize. 5.36 and 1.6. Okay. It should look like this. And then 3, 6, 3, 5, and 2 are using natural rounding. So rounded up, rounded down, rounded down, rounded down, rounded up. And we still only, now we only get 19. So 3, 6, 3, 5, and 2. So now we notice that at 12,000, we had too many. Now at 12,500, we have too few. So we have to go somewhere in between 12,000 and 12,500. So I'm going to give you a little hint to move this along. We're going to use 12,250. Okay. And that should do it. So let's go back to Desmos one more time. And I'm going to create one more column here and say X1 divided by 12,250. And you can see that we get 2.61, 6.53, 3.35, 5.47, and 1.63. And then when we use our natural rounding rules here, these will naturally round appropriately. So this one rounds up, rounds down to 5, and this one rounds up to 2. So now we add these and we get 20. Woohoo! We got it. So I really suggest that you work through the did you get it? Because you can have the answers right there to make sure you're doing each of the parts correctly. The original standard divisor, the Hamilton's method, the Jefferson's method, and then the Webster's method. And if you go ahead and try the worksheet for 1-7, just to give a heads up on the 1-7 worksheet, I would use, if you come up with a decimal for your standard divisor, just round it to the nearest whole number. That's what I would do. And have a blessed day. We'll catch you back for unit 2.